All right, everybody, so welcome to Odysseyware video number 3. Today we're going to be looking at the second lesson under the Introduction to Waves unit on Odysseyware, and this one is called a wave phenomena is what this is called. So I'm noticing this trend with Odysseyware where the first section is talking all about vocabulary, and it asks you a whole bunch of questions about vocab. For some of you guys, that's going to work just fine. For some of you, though, you're like me, and you don't want to hear the vocab first. And so you might want to start getting in the habit of skipping to section 2 if you can, and starting there. Either way, even if, I don't actually know if you can do that. Even if you can't do that, I'm going to skip it. We're going to talk about the other things. And I think that'll help you as you go back to section 1 and try to do the vocabulary. Okay. So basically what this section is talking about is weird stuff waves do, okay? That's what wave phenomena means, weird stuff waves do. And so the first two things we're gonna be talking about are reflection and refraction. And to be honest, the questions at the bottom don't really focus on refraction, and I think that's probably a good thing. We will talk about it briefly, but what we're really gonna focus on is the idea of reflection, okay? So this is really important for our initial vocab. We've got this picture here that shows a wave traveling toward a wall, okay? And what's going to happen is that wave is going to bounce off of that wall and come back, okay? And we've got some words here up in this section. So we've got the incident wave. The incident wave is the one coming in, right, toward the material, and then you have the reflected wave. So the incident wave, and then it hits something and it bounces back. You get the reflected wave off of that surface, okay? And so what you're gonna see here is that in this case, the incident wave is a crest, but when it bounces off this wall, the reflected wave is a trough. And that is kind of one of their big ideas is when is the incident wave or when is it going to be, this is called inverting the wave. So flipping it upside down is inverting it. When is the wave going to get inverted, and when is it not going to get inverted is going to be your big question here. In order to answer that, I have a little simulation here that we're actually going to look at. So we're looking at this simulation. This is the wave on a string. You probably played with this in your physics class, but we're going to use it a little bit differently this time. And so what we're going to see is that right now we've got it set at fixed end. So you can see this is like a string, and we've clamped the end of the string so that it doesn't move. So we're going to send one wave pulse. I'm doing it in slow motion. And so here's our incident wave coming in toward the end. When it hits, it gets reflected and inverted. So it goes from being a crest to being a trough. All right. What if we have a loose end? What if the end of the string is free to move however you want? Well, let's see what happens there. When the end is free to move however it wants to, it's going to hit and it's going to be reflected as a crest still. So it will only be inverted if there is a solid sort of connection at the end of the wave. All right, well, what we're really going to be talking about in these sort of questions and in the next step is we're going to be talking about a wave moving from one material into another. And so the key here is that idea of like, if the end is loose, then the reflection is no inversion. It just stays, it was a crest and it stays a crest. If the end is solid, it's going to become a trough. So what I want you to think about is this. So imagine this picture in your head. It's summer, right? So it's a sunny, hot day, and you're standing at the pool. And the sunlight is shining down and it is hitting the pool, all right? Does sunlight get reflected off the surface of the pool? Yes, it does, right? You can see the reflections of the light on the surface of the water. Does sunlight also go into the pool? Yes, it does. So the light is hitting the surface of the water, and some of it bounces off and some of it keeps going. Okay, so that gives us a reflected wave and a transmitted wave. Okay, all right, so what we need to know is that when we go from air into water, you're traveling from a less dense to a more dense material. Okay, and so what we're going to see is, since we're going into a more dense material, that's like hitting that firm fixed end. Water doesn't vibrate very easily. And so it's going to look like this picture up here. You're going to have the incident wave is going to hit. The reflected wave will be inverted off the top of the water. Okay? The transmitted wave is going to stay the same because the transmitted always stays the same. Okay, so your big ideas now. The transmitted wave, the one that goes into the water or into the new material, always stays the same. The reflected wave, if it's reflected off a more dense material, will be inverted. That's this first picture. This picture right here shows what would happen if you hit a less dense material. Okay, so if you send this slinky, this like really heavy slinky, into this much less dense string, you'll actually see a reflection when it travels from the slinky to the string because there's a change in material. But since the string is less dense, it acts like that free end and the wave is not inverted. Okay, so more dense, you get inversion. Less dense, no inversion. Okay, that is the secret. If we look down at some of these questions down here, it really talks about that a lot. These super complicated questions to understand, but you've just got a bowl of gelatin in a pan. And it's just, the important thing is this is not very dense, more dense, very dense. So it's saying you've got a wave, just a crest, traveling from, look, it says right here, the first pulse generated extends from the front end of the pan to the blue-red boundary. So it's going from here, from the blue, toward the red. You got to ask yourself, is it going to become more dense? Yes. And so the reflected light off of that boundary is going to be inverted, right? Look up here, right? Reflect, if we're going to a more dense material, it says it right here, it's going to be inverted. So this first one, we're saying the reflected pulse, it was a crest, it's going to be inverted into a trough. Okay. If we go to the next one, now it's still talking about the blue-red boundary, but now it's talking about the transmitted pulse, the one that goes in. Well, it was a crest, it's going to stay a crest because the transmitted pulse always stays a crest. Okay. And so you would just say crest for that one. And then it's going to keep asking you about each boundary, and then it's going to reflect off the other side, and it's going to keep asking you about each boundary. All right. So you got to, this is another one where drawing a picture might be super helpful. All right. So we're 8 minutes in. Those are really hard questions here on section 2. So I wanted to spend a lot of time on that. In these other sections, the biggest thing I really wanted to focus on, if you actually look at the questions for section number 3, it has a ton of information about diffraction and interference. And if you're getting ready to do your vocab, you want to know what those words mean. But what I'm going to focus on is this very bottom part that talks about standing waves. Okay, so I'm going to show you what a standing wave is really quick, and then we're going to talk about how to do calculations for standing waves in just a second. Okay, so we're going to change this and we're going to go to oscillate. We're going to go to no end. So right here, or sorry, we're going to go to fixed end. I apologize. So what we're going to see, we restart it, is we're going to send these waves out and they're going to reflect back off, right? Well, when they reflect, you're going to have a wave, an incident wave going this way and a reflected wave going this way. Those waves overlap each other, okay? And they do what's called interference. If a peak of a wave and a trough of a wave hit the same spot, I can actually show you this, hold on. At the same time, then they will interfere with each other. Watch this. So you've got the peak of the reflected wave here, or so the peak of the incident wave, the peak of the reflected wave, and as we play it, they're going to cancel each other out for just a moment. Because you've got a peak and a trough at the same place, they cancel each other out. That's called destructive interference. If we change this to a loose end, we can see what happens when two waves that are both crests arrive at the same spot at the same time. So again, we're going to have our incident wave and our reflected wave. And when they run into each other, they make a bigger peak. This is called constructive interference, right? So if we set this up so it's constantly sending waves, you constantly have a incident wave and you constantly have a reflected wave, and they're constantly overlapping each other. And what you get is a phenomenon like this called a standing wave, where it looks like the wave is just staying in place. It looks like nothing is moving. Okay, that's called a standing wave. Really, you have waves going this way, waves going this way, they're overlapping, but it looks like nothing is happening. It looks like it's just sitting there. All right, and so you're gonna be asked a lot of questions about standing waves on your Odysseyware work, and the secret is right here at the bottom, okay? You've got this example question, and it says, in establishing standing waves with a slinky, your wrist oscillates, moves, with a frequency of 8 hertz. You're making 8 waves a second. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And the length between 2 consecutive nodes, a node is like the space between the waves, is 2.5 meters. So in other words, your wave is 2.5 meters long. That's the wavelength. And you have a frequency of 8 hertz. Okay? And it says, what is the velocity of the wave generated? You got a bunch of questions like this. Guys, you know how to do this. You know that it is asking you to just use the equation, right? You're going to use the frequency and the wavelength, and you're going to multiply them together to get the wave speed. The only trick that it's trying to play on you is that if we go back and look at my other example really quick. All right, so here's my standing wave again. What we have, I actually need to change this so that it's actually a standing wave, because right now it is not. Hold on, it's gonna look weird. I gotta get it to be a standing wave. It's hard to make standing waves on the computer. It's really easy to make them with an actual piece of paper or with an actual string. I don't know why I said piece of paper. That didn't make any sense. Anyway, here's what I need to tell you. Here, let's do this. On a standing wave. There we go. That's what I need. You're going to have these spots. Here we go. And you know what? Actually, let's use this guy. So you see on here, you're going to have spots where the wave is going up and down, up and down, up and down. You're going to have other spots where like no motion seems to happen at all. These spots are called nodes. Okay, so it told you in that problem, the space between 2 nodes is 2.5 meters. Okay, so this is 2.5 meters. Here's the problem. That's not a whole wavelength. That's just half of a wavelength. Okay, you actually have to go from this node to this node to this node. You need 3 nodes to find the full wavelength. Okay, so if we go back to the problem, and it does actually explain it to you, but it would have been easy for you to overlook this sentence. If we go back to the problem, it says, since the length between 2 nodes is half the wavelength will be 2.5 times 2, or 5. All right, so that's the only trick it's trying to play on you, is that it's giving you only half the wavelength. And so you're going to go, okay, well, it's a wavelength of 5. I'm plugging it into my equation. Here we go. Wavelength is 5. I'm plugging in my frequency as 8, just like I did before. I'm multiplying those together to get 40. Okay. You have a bunch of questions down here, right? Question 11 is asking you to solve for velocity. Question 12 is asking you to solve for frequency given the wavelength and the speed. Question number 13 is asking you to solve for frequency given the wavelength and the speed. So there's a bunch of these that are doing that on this section, okay? There's definitely some more vocab that you need to review, and I'm going to leave you guys to kind of look for the vocab and practice that. Remember, you can go to section 1 and you've got your whole list of vocabulary here. You also can do the vocab arcade flashcards to help you. But I really wanted to help you with questions like this one, where it's talking about the transmitted or reflected pulse. And I really wanted to help you with questions like this one, where it's asking you to use the equation again. It's just being tricky. Good luck.